Hello and welcome. My name is Samiksha and I'll be presenting our time series analysis project titled Assessing the Accuracy of Forecasting International Airline Passengers over the Next 10 Months. This research is a part of our Math 1318 time series analysis coursework conducted in collaboration with my teammates Nazia Ali and Omkar Salunkhe. We used a well known dataset, monthly international airline passenger numbers from the year 1949 to 1960, sourced from Jason Brownlee's repository on GitHub. It contains monthly frequency observations over 12 years, totaling 144 data points. Our main aim is to forecast passenger numbers for the next 10 months using ARIMA modeling. The visual inspection of the data revealed several key patterns. First, there's a clear upward trend which reflects the steady growth in international travel over time. We also observed strong seasonality with regular peaks and lows occurring roughly every 12 months. Additionally, the variance increases over time, indicating that the data becomes more spread out as passenger numbers rise. The series also shows characteristics of both autoregressive and moving average behavior. Lastly, we identified a change point where the rate of increase in passenger numbers becomes noticeably steeper, signaling a shift in the underlying pattern. We also performed several statistical tests to confirm what we saw visually. The augmented Dickey-Fuller test gave a p value of 0.01. Although this is low, the data is still considered non-stationary due to the presence of both trend and seasonality. The ACF plot showed a slow decay, further confirming the presence of a trend. The PACF plot had a large spike at lag 1, pointing towards an AR1 structure. These findings highlighted the need for differencing to remove both trend and seasonal components before fitting a model. Further, based on insights from ACF, PACF, EACF, and BIC tables, we explored three potential ARIMA models: ARIMA 111, 011, 12, ARIMA 011, 011, 12, and ARIMA 110, 011, 12. Each of these models incorporates a seasonal MA component to effectively capture the yearly cycle in the data. We implemented these models using ARIMA function in R. To determine the most suitable model, we assessed both the visual fit and the key statistical indicators for each candidate. Although we initially started with ARIMA to model the trend and structure in data, but due to the presence of strong yearly seasonality, we moved to SARIMA, which allowed us to incorporate seasonal components and differencing for a more accurate and reliable forecast. Next, we implemented coefficient significance testing using the coef test function from the LM test package. In the model 011, 01112, the MA1 term was highly significant with a p-value less than 0.001. In contrast, the other models had insignificant coefficients including the AR1 and seasonal MA terms. This made the 011 01112 model both parsimonious and statistically reliable, so we selected it for further forecasting. Additionally, we ran diagnostic tests to ensure our model met the assumptions of SARIMA. The Leong box test returned a p-value of 0.43, indicating that the residuals are uncorrelated, which is a good sign. Although the Shapiro-Wilk test gave the p-value of 0.0125, suggesting mild deviation from normality, the histogram and the QQ plot confirmed that the residuals were reasonably symmetric. Overall, the residual diagnostics confirmed that the model fit was statistically adequate. In conclusion, our analysis showed that based on thorough model identification, parameter estimation, and residual testing, we found that Serima 011 01112 was the best fitted model. The model captured both trend and seasonality in the data effectively. Our forecast for the next 10 months reflects consistent seasonal patterns with a reasonable level of confidence. So, to answer our research question, yes, we can accurately forecast international airline passengers for the next 10 months using our selected Sarima model. Thank you for watching.